Hello, everyone, and welcome back to your channel, Math Made Easy. If you remember last session, we did the centroids and we did centroids of simple shapes like triangles, rectangles, n-degree parabola, semicircle, quadrant, semi-ellipse. And then after that, I said today I'm going to start with what we call the centroid of composite shape. So here's an example. This example can be solved. I will show you how easy it is when we break this composite shape into simple shapes for which we know if you know the area, the location of the centroid, x bar and y bar of each shape, then you can solve any composite shape. How? So let's do that by constructing a small table. So let me just use this pencil. So I will construct a table, and this table I'm going to divide it into pretty much like 6 columns. The first column I'm going to say shape. Okay, so shape. Then I will do the area. Then I will do the X bar of each shape. And after the X bar, we are going to do something, we are going to call it my, or the moment about the y-axis. We'll see what that means. And then we'll do a column called y bar, and finally a column that is called mx. What we are going to do is to number the shapes. So rectangle is pretty much the easiest one. So I'm going to give it the number 1. Triangle is the second. I'm going to give it the number 2. The quadrant is the third. So I'm going to give it number 3. And what is that? That's a semicircle that is cut from so this is a plate in this shape. And after we did it, we said, you know what, for some reason, some maybe manufacturing reason, we cut a semicircle here. And I ask you for the remainder of the plate. So this shape, I'm going to call it -4. Why negative? Because we cut it. Okay. So I can remember always that this is cut. So let's start with shape number 1. So here is shape number 1. I can find its area, its base times height, 6 times 3. So I can write 18. Then I go to the triangle. Half base times height. Base is 3. They didn't give me the height. What is the height? Yes, the quadrant has a radius of 3, meaning this distance is 3 and that distance is 3, but that's the height of both the rectangle and the triangle. So shape number 2 is 1/2 times 9, which is 4.5. Number 3 is a quadrant of radius 3. Pi r square is 9 pi, but this is just a quarter of a circle. So 9 pi over 4, and I'm not going to evaluate it. I'm going to leave it as that. And you will see why later. And finally, I have 4. I'm going to call it -4, so I don't forget the negative sign here. I cut a circle, a semicircle. If it were a circle, pi r square would be pi because r is 1. But this is half a circle, so it's -pi over 2. And now I can use my calculator to find the total area. Okay? So I will need the total area, the total my, and the total mx. 22 and a half plus 9 over 4 minus 0.5 or minus 1 half pi, right? 2799. And let's say 28. It doesn't matter because I'm not going to use this number. I have it stored in the calculator. I will do the same thing by starting with x bar. Notice this the origin is here. Here's the x-axis, here's the y-axis. So the centroid of the rectangle along the x is half the base, which is 3. For the triangle, it's not 1/3 of the base or 1. Because I didn't ask you what is that distance. I said, what is the coordinates? I have 6 plus 1. So it's 7. This is a common mistake. That's what the first common mistake I see is that the student, they say, oh, it's 1/3 the base. The base is 3, so it's 1, and they write 1. So what is, there is no difference. Do you think there is no difference if I put the triangle here or put it there or put, no, of course. The further it gets, the more like the more rotation of the plate it would have possessed, which in engineering we call it the moment. It has a higher moment, right? The closer it is to the y-axis, the less effect it would have about the rotation of the plate. So I am not interested in that distance. I'm interested in the coordinate, the x and the y coordinates of the centroid of this particular triangle, not any triangle that has a base of 3 and a height of 3. Okay, let's move one step down and we see what is the centroid, the x coordinate of the centroid of this quadrant. If you go back to the table we did, it tells you that the centroid is at 4r over 3 pi. The radius is 3, so 4 times 3 over 3 pi. The 3 and the 3 cancel and you get 4 over pi. And how about the centroid, the x-coordinate of the centroid of the semicircle? Of course, it's 0. Why 0? Because it is on the y-axis. The centroid is on the y-axis. So how far from the y-axis it is? It's 0. And now it's a matter of multiplication. 18 times 3 is 54. 4.5 times 7 is 31.5. Pi and pi cancel, 4 and 4 cancel, I get 9. 0. So I add them up, 85.5 minus 9 is 76.5. Or you can use the calculator and say 54 plus 31.5 plus 9 equals, oh, minus 9, not plus 9. What am I doing? 76.5, like we said. 76.5. If you want the units, they are cubic inch. Why? Because the area was inch square and you multiply by a distance, which is inch. Again, it's not important, but that's to be consistent. Okay. Now I want to stop here and say, I said I created something called my. What does that, the moment, mean? The moment means the tendency of a force to produce rotation about an axis. Okay? But where is the force? I don't have force. Yeah, I know. This is a plate, right? If this plate is homogeneous, meaning made all of it of the same material, steel, aluminum, you name it, cardboard, it doesn't matter. And if its thickness is uniform, it doesn't change. It's not thicker in one place, thinner on another. No, it's the same thickness, same material. Then the area would be proportional to the volume. And if it's of the same material, then it has the same density, then it has the same weight. A weight is a force. So I will assume this is made of a material. I don't care about the density. I don't care about the thickness, but I'm going to say the area is proportional to the weight. And this weight is what it that tries to rotate this this plate about the y-axis or about the x-axis. Okay? So that's why I said a moment. Now, it's not a theorem, it's common sense. We say, if I take the whole plate, whatever its shape is, and multiply it by its x coordinate of the centroid, that produces a rotation about the y, correct? Good. But that rotation would be equivalent to the sum of the rotations of each of its parts is producing about the y-axis or the x-axis or any other axis. I say it doesn't matter. I can take the small pieces, see how each one rotates, add them up, or I can get the whole thing and see how does it rotate. And because I don't know where the centroid of the big piece, I say, okay, if I knew it, if it's an x bar for the whole shape, then 28 times the x bar must equal the small areas times their x bars. So in order to find x bar, I say it's my over the area. That's it. And that's why I took the total and I said 76.5 divided by 28. I don't need to divide that. I can use 76.5 divided by 27.99, whatever. Oops, did I divide? I didn't divide. This divided by that. And I get 2.73 inches. So slightly to the left of the centroid of the rectangle. Why slightly to the left? Well, I don't know, but it seems like if these two things were producing the same rotation about the y-axis, then they cancel each other and I would have gotten 3. But since I get slightly less than 3, then this thing is producing more rotation about the y than that, so it's shifting it a little bit like that to the left. It's not a big deal, but that's the explanation. Yes, this is further away, so you should expect it to produce more. In fact, it's multiplied by 7, and this is only multiplied by that, but you know, it so happened that we ended up slightly to the left of 3. Now let's go to the y bar. Now I'm looking at how high the centroids, the 4 centroids, are from the x-axis. If this height is 3, then you get 1.5. If this height is 3, you get 1. Here I don't need to add anything. Here we added 6 to the x, but in the y it's just 1. It's 1 inch above the x-axis. When I get to the quadrant, it's the same number. Oh, you see what I did wrong here? This was a negative. And I was subtracting, but I forgot to write it. I said 85.5 minus 9, but I wrote it 9. You see, the centroid in the x direction is to the left of the y, so it's negative. But in the y, it's above the x, so it's positive. 4 over pi. I'm sorry for that. I don't know how I forgot to write it. Then the centroid of the y coordinate of the centroid here, notice it's above the x, so it's 4r over 3 pi. R is 1, so it's 4 over 3 pi. 4 over 3 pi. And here comes the second error I used to see a lot in homeworks, and that's why I stress it so that the kids, when they go to the test, they do it correctly. Is that many students would write it as negative. When I ask them, how on Earth is it negative if it's above the x-axis? You say, no, no, no. We cut the circle, so it's negative. I say, yes, the area is negative. We already wrote that. But the centroid is positive. If you write it negative, you see the negative and the negative cancel each other, and you will be, it's as if you did a rectangle and a triangle and a quadrant, and then you added another plate here that in the shape of a semicircle. If I attach and glue a semicircle on the plate, that would be positive and positive. So if you make it negative and negative, that becomes an extra semicircle, not cut semicircle. You cut it only in the area. And then if it's to the right of the y-axis, x bar is positive, to the left is negative. If it's above the x, it's positive y coordinate. If it's below, it's negative y coordinate. Take it as it is, and it would correct itself. Don't worry about plus or minus. Sorry again for this mistake. That's horrible mistake. I should have written that correctly. Now, I'm going to multiply the area by the y bar to get the moment about the x. Notice that the moment about the x will give me the y centroid. 18 times 1.5 is 27. That's half of 18 times 3. So, and half of 54 is 27. 4.5 times 1. I think I need a calculator for this one. And since this was a negative 9, that is a positive 9, right? Oops, it doesn't matter. I used a different color. And then here I have a negative. Pi and pi cancel. 4 and 2 becomes 2, so this is negative 2/3. Now, 40.5 minus 2/3, or 27 plus 4.5 plus 9 minus 2/3 equals 39,833. And y bar would be mx over the area equals 39.8 over 28 equals, and then you take this divided by that, it gives you 1.42 inches. Again, slightly lower, very slightly lower than the centroid of the rectangle. So to the left and below is, excuse me. So if you take this shape exactly and you hang it with a cable at these coordinates, it would remain horizontal. It's not going to tilt in this way or in that way. It would stay horizontal. Okay, that's the first problem. As you can see, if you know the area and the x and the y of each area, their centroid, you can use simple math to do it. Okay, the second example I wanted to go over is a little different. I have a second-degree parabola on the top of this plate and a triangle at the bottom. And here I'm going to introduce a method to do it with integration. Okay? And then I will tell you, remember what I gave you last time when I told you I can find the centroid of any degree parabola? I will show you that we didn't really need integration. So let's do it first with integration, and let's define x bar and y bar. We are going to say x bar equals the integral of x dA over the integral of dA. What does that mean? Remember when we said that there is, how did we find x bar of the composite shape? I said it's the x bar of each shape times the area, x bar of each shape times the area, divide, and then at the end I divided by the area. I divided by the area. So instead of summing when the areas were discrete and I know everything about them, here I use integration if I assume that even if I know the area, it's fine. I still can integrate it, but if it's hard, it's better. Maybe it's better to integrate. We'll see that. Now, but how do I write it? Remember in integration, if I want to integrate a shape like that, I don't have to make each one separately. Why? Because if you look in the y direction, this curve is always above that. If I look in the x, no, they are not. If I go into the x, I will do this one first and then this one second and add them. So it may make sense to take the strip in the y, right? So if I take a strip in the y like that, and I make the base as dx, remember, dx is the limit of delta x as it approaches 0. So even though this shape at the bottom, it looks like if this point, this is slightly curved, or if it's a straight line, that would look like a trapezoid. But if we get x very small, delta x approaches 0, then that becomes a rectangle. And this rectangle has a height of y1 minus y2. Okay, so let's calculate the area first. The area is the integral. Notice I'm integrating with respect to x. dx. I'm starting from 0 to 2. Here, all the distances are 2. So 0 to 2. What is this rectangle? Its height is y1. I have y squared equals 2x. So y equals plus or minus root 2x. The plus is this. The minus if I had a whole parabola. So I don't have the negative. It's just root 2x. So it's square root of 2x minus negative x, so plus x. It's that simple. And this is dx. So dx is the base, y1 minus y2 is the height. And you are accumulating them by taking the integral. It's so easy. Now, square root of 2 is a constant. And this is x to the 1/2. So when you integrate it, you get x to the 3/2 over 3/2, meaning times 2/3, plus x squared over 2. And you evaluate that from 0 to 2. And since both terms, when x equals 0, become 0, you don't need to say, oh, the top minus the bottom. You just evaluate it at the top. X is 2. 2 to the 3/2, meaning 2 square root of 2, right? And there is another square root of 2 that would make it 4. And there is another 2, so that makes it 8. Root 2 times 2 times 2 times root 2. It's 8/3 plus x squared is 4 over 2 is 2. 2 is 6/3 plus 8/3 is 14/3 square meter. That's the area. Notice that y bar likewise would be the integral of y dA over the integral of dA, which, so this one serves as the denominator of both x bar and y bar. Now, let's find the integral of x dA. Well, I have dA, so I'm simply gonna multiply it by x. So it's the integral from 0 to 2 of x times the square root of 2x plus x squared. So I multiply this function by x dx, meaning I can rewrite it as root 2 is a constant. X to the 1/2 times x is x to the 3/2 plus x squared dx. Root 2 times x to the 3 halves. You integrate it, you add 1, so it becomes x to the 5 halves divided by 5 halves or multiplied by 2/5 plus x cubed over 3 from 0 to 2. And again, I don't care about the 0 because it's 0. So x to the 5 halves is x to the 4 halves, meaning x squared, times root 2. 2 squared times root 2, right? 2 squared is 4. 4 root 2 times 2 is 8 root 2 times root 2 is 16/5 plus 8/3 cubic meter. I don't care about that, but, and then finally I get x bar by dividing this number by the area. So 16/5 plus 8/3 divided by 14/3. I get 1.26 meter. I was going to write inch. It's more than 1. Does it make sense? Always ask yourself this question. Yes, absolutely, it makes sense. Because 1, meaning halfway between the support and the end of the plate, if I take a distance of 1, definitely the right-hand side would be heavier than the left-hand side, and it would tilt this way. So the centroid must shift to the right more than 1. So if I got an answer of 1 or a decimal less than 1, I know I did a mistake. That doesn't guarantee that you did it correctly, but at least it makes sense. So you are at least, you say that most likely, or I don't know, you cannot say even most likely, but you see, at least we are on the good side. We know it's more than 1. How about y bar? Do you expect it to be positive or negative? Think about it. This is 2, this is 2. That's a triangle, that's a second-degree parabola. If you said positive, you would be correct. Why? Because if I join these 2 points, I have a triangle and a triangle, they cancel each other. So if I only had that, the centroid would be exactly on the x-axis. But since there is a small piece, then I think the centroid must shift slightly above. Probably won't be a big number, but it wouldn't be negative. Or else, again, I would have been I'll be doing an error. The integral of y dA, meaning, notice here is the area. The centroid of this area is on this line that is x away from the y-axis. That's why I multiplied by x. But where is the centroid of this rectangle? Yes, it's midway between this point and that point. This point is y1, this point is y2. This is root 2x, and that's negative x. So when you say this minus that, I'm sorry, this plus that, the plus becomes a minus, right? Because it's a negative x. So you say root 2x plus negative x, which is minus x, over 2. Over 2 is 1/2, so that's a constant. So I'm going to take it out. And then take the integral from 0 to 2. The area, as we said, was 2x root 2x plus x. And this area would be multiplied by the y bar of the rectangle, which is y1 plus y2 over 2. Notice plus y is negative x. But when we did the area, we said y1 minus y2, so the negative changed that into positive. But look at that expression. It's a plus b times a minus b. And we know that when you multiply them, you get a squared minus b squared. So really, that's a very simple integration. You get 2x minus x squared dx equals 1/2 times the integral of that is x squared. The integral of that is x cubed over 3, evaluated from 0 to 2 equals 1/2 times 4 minus 8/3. 4 is 12/3 minus 8/3 is 4/3, and 4/3 times 1/2 is 2/3. So y bar becomes 2/3. In fact, it's 2/3 divided by 14/3, so times 3 over 14 is 1/7 meter, which is 0.142857. So that's y bar, which is slightly more than 0. We expected it to be positive, but not a big number, because these two areas are pretty much equal. The top is slightly more. I told you earlier, we are done. So we solved the two examples I wanted to go over today. However, I wanted to show you that we really didn't need integration with the information I gave you last time. Let me redraw that quickly. I'm not going to draw it to scale, so I'm going to say I have a triangle here of height 2 and a base 2. Well, it's not to scale. And then I'm going to say, well, the top was a rectangle. Well, in fact, it's a square of height 2 and base 2. And then I cut from it this side. So I'm going to call this 1. This is 2, and that's -3. 2 is the whole rectangle, okay? So this is the rectangle. So like we did before in the first example, I'm going to say shape 1, 2, -3. And then I'm going to say the area, the x bar, my, y bar, mx. It's not going to take long. And then I have total area, total my, total mx. Let's do the areas first. That's a triangle. A base of 2, height of 2, 2 times 2 is 4, 1/2 of that is 2. How about the rectangle? 2 times 2 is 4. Of course, twice the triangle. And do you remember the second degree parabola? I kept this from last time. The second degree parabola, its area is BH over 3, n plus 1. So 1/3 base times height, 4, it's -4/3. So 6 minus 4/3, 6 minus 4/3 is 4 2/3. 4 2/3 meaning 14/3, exactly like before. Oh, sorry, we already have it here, so let me put them next to each other. 14/3, 14/3. Now, let's look at this, the x bar of the centroid. For the triangle, it's 1/3 always from the right angle. So this distance is 2/3, and that distance is 4/3. 1/3 of the base, 2/3 of the base. Be careful. We always calculate from the right triangle. This triangle, the centroid is at 2/3. This triangle, the centroid is at 4/3. Okay? So be careful how we do it. So this is 4/3, the x bar. How about the rectangle? It's 2, so 1. How about the piece that we cut? Two things you have to worry about. First of all, we drew this as a second degree parabola, so this is the first degree, that's the second degree parabola that we plotted here. Not this. You cannot use that. You have to turn it 90 degrees, and now the x bar and the y bar would be backwards. You see that? I didn't draw a second degree parabola from here like that, or like that. No, it's the other way around. So when I say x bar, I look at the y bar. It's 3/10 of the height. The height is 2 in this case, okay? But notice, it's 3/10 of the height, which is 2. So some people would say, well, 3/10 of 2 is 3/5. Is that correct? Hmm. I'll keep it and let you think about it. This is but this is the x. Yes, it's 3/10 of 2, right? 3/10 of 2 is 3/5 or 0.6. Let's write it 3/5. And now I can multiply to get my. This is 8/3. This is 4. The 3 and the 3 cancel, and this is negative 4/5. So let's calculate that. 8/3 plus 4 minus 4/5 equals 5.866. What did we have here? Oh, we had the sum of those. So let's divide this or multiply it by 3/14. 1.257 or 1.26, exactly the same. Exactly the same. So x bar equals 5.866 over 14/3 equals 1.26 meter. Now let's do the y bar. Y bar of the triangle, it's below, it's negative 2/3, right? The y is still 1 because it's above half, because that's a square, not a rectangle. I said rectangle, but we said square. And how about this guy? The centroid of this is b over 4, right? But b over 4 from the right angle. That distance is 2. B over 4 is 1/2. So should I subtract, I'm sorry, should I say 1/2? What do you think? Here is the centroid. That distance is 2 times 3/10, and that distance is b over 4, 2 over 4, which is 1/2. But that height is 2. So the coordinate, the y coordinate of this point is 2 minus 1/2, is 3/2. Now let's multiply and find the mx's. Negative 4/3, positive 4, negative 2, right? Negative 2. The 3 and the 3 cancel, and negative 4 over 2 is negative 2. So you get 2 minus 4/3. 2 is 6/3 minus 4/3 is 2/3. Guess what? 2/3. So when I divide, I get y bar equals 2/3 divided by 14/3 equals 0.1428 or 1/7. Exactly the same. Exactly the same. The only difference is that you see how this second degree parabola is plotted? It's like this guy. So that's the confusing part, is that my x bar becomes y bar and y bar becomes x bar. But again, as I said, if that's confusing, you already learn how to do it using integration. I could have used even integration here, believe it or not. But for the circle, maybe we can do uh, excuse me, we can do polar coordinates or something. In fact, you don't need it because you know the area and the centroid of a triangle, a rectangle, a circle, semicircle, and we learn all of that. I hope this was good enough because that concludes the topic of centroids. This lecture, of course, was much longer than the previous one because you have to do two examples or three to tell you because we did one in two different ways. I hope this was helpful. Again, if you have any questions or comments, please add them to the comment section. I'd love to respond to you as soon as I can. Otherwise, I wish you all the best and see you soon. Bye.